In the 60s, computers were powerful and expensive, but spent much of their time idle, waiting while the person using them thought. ARPA wanted to know how to get several different users working at the same time. Unbeknown to ARPA, the answer to this question had already been worked out in England at the National Physical Laboratory by a mathematician working on the theory of queuing up.
Queuing theory became essential because of the amount of traffic that was trying to use one switch. Clearly, if you have lots of messages coming into a switching center and being sent out to lots of different places, they have to queue up for service by the various lines. Now, I happen to know a bit about queuing theory, and it turns out that queues really have only two kinds of states. They're either relatively small and the network operating fairly well, or the network has already got overloaded, far too much traffic has come in for it to possibly be capable of handling that traffic. And so the queues are building up to infinity, and in fact the whole thing is completely wasted, useless, because it's congested. Essential requirements to prevent the queues from getting very long and the whole thing getting very much delayed. One of them is to have very high-speed lines. The other essential thing was to have very short messages, or packets.
Packet switching has two very interesting features that make it so effective, so efficient. The first is the concept of sharing communication lines. You know, when you and I talk on a telephone line, if we stop talking, we're still tying up the connection. In packet switching, that's not the case. You only use the connection when you're actually sending data.
Well, thank God I found a phone booth.
See, data traffic is highly bursty, which means we send some and then we stop for a while. I type a few keys and maybe get a file back, and then I stop and I think for a while. And when we're not sending data, someone else can send data along that same piece of communications line. And that's the beauty of packet switching, resource sharing. Now, the other thing about packet switching is it takes a long message and chops it up into little pieces. And each piece travels through the network independently. It has an address saying where it wants to go. And each of these switches looks at this little packet that comes in, looks at the address, and says, ah, you go that way. Another packet may go that way because maybe that line got busy or broken. So these packets sort of meander around the network, intelligently being routed toward the destination. At the destination, they all get collected together again and delivered to you as a picture, as a file, or whatever.
I think the ideas were so revolutionary that it needed something like ARPA had, which was a few £1 million, a few $1 million that you could throw at the problem without having to justify it.
Which is exactly what ARPA had done. In 1969, the very first packet switch, the interface message processor, arrived in his lab. This was the very first piece of the net. The very first connection on the ARPANET was ready to be made.
This machine first arrived the weekend of Labor Day, 1969. It was small, size of a telephone booth, as you can see. This was state-of-the-art. My wristwatch contains more capacity and capability than this machine does now. When Stanford Research Institute got the second one of these babies, we could then communicate. Basically, we did that out of my laboratory in October, early October, '69.